Welcome back. And the title of this is Area Between the Curves, More Cleverness, which I guess means we're going to work some harder problems and show you some of the little gotchas that you might run into. But when you think about what we've done, think about how we formulated the integral that we were taking. This should make sense to you. But let's go through one of these problems. This is in your book. Page 352, number 18, they gave us two curves, y equal 8 minus x squared. Okay, I can draw that one. Y equal x squared. And they said they wanted to find the area between the curves from x equal to minus 3 to x equal to 3. Okay, first thing we need to do, and we really got to do a good job getting a good picture of this. If you don't get a good picture, you won't see the problem you're running into. So, x minus 8 squared, that's, to me, is going to, I know that's an upside down parabola, okay? So this is my curve here, 8 minus x squared. So first guy gets a picture, solves the problem. I used to tell engineers at Qualcomm that. We get a good picture here, y equal x squared here. Don't think I need my update. Oop, cancel that. Okay, this is what? This is y equal to x squared. All right, now they want to go from 3. Now the question is, well, where do these guys intersect? That's one of our problems here. Where do they intersect? Well, how do you find out where they intersect? You set them equal. Where's 8 minus x squared equal to x squared? Well, here I'm going to say, well, that's 8 is equal to 2x squared. 4 is equal to x squared. X is going to be equal to plus or minus 2. So this must be 2. This must be minus 2. But they want me to go from what to what? Well, I'm going to get a different color here. They want me to go out here to 3. And I don't really know if I've drawn that right there. That's probably doesn't mean it went down. They want to go out to here, okay? So, couple things that go on here. Let's draw some rectangles. I can get this rectangle here. That's easy. That was my standard one. But then I got to get this rectangle here. Okay, so I got a different rectangle. I get a rectangle here. I'm going to apply some symmetry here. First thing maybe you can see, could you see the following? Can you see the area? This is an even function, and let's take care of the first problem first. Let me stay focused. If I want to find the area here from 0 to 2, well, that's easy. I could do this. I could go from 0 to 2. Now notice it's x equal, because I'm integrating dx. What is the height of this rectangle? Well, that's going to be 8 minus x squared, right? The top part of the curve minus the lower part of the curve here, x squared. Okay, that dx, right? I'm going to integrate dx. That's going to give me, I get some colors here. What? That's going to give me this area here. Right, I'm going, my rectangle start at 0, and they go to 2. All right. Now, well, what happens when at 2, you see the y equal x squared is the top curve. So I need to add up. I need to add this second integral. I'm going to need a second integral. It's going to go from where to where? Well, it's going to go from x equal to 2 to 3. Now what's the height of the rectangle? Well, it's x squared minus the bottom curve, 8 minus x squared. Okay, so I just found, so there's a couple of things here that made this tricky. I had to break it up into 2 integrals. Now the other thing to see, well, they want the area from minus 3 to 3. And can you see the symmetry here? Basically, the area on the area from 0 to 3 is the same as the area from -3 to 0. So I'm going to put a 2 out here. I'll just put a 2. Because remember, what made a lot of my problems easy to evaluate was the fact I have a 0 at the bottom. Ooh, that's not quite as easy. I got a 2 here. But putting a 0 in the lower half really helps things. And here I avoid doing the same. I cut down my amount of work in half. Okay, so I'm just going to, I think I'm going to leave that there. You can integrate that. I know I could get that right. And again, we will, even when I test you, I will sometimes tell you to set up. I'll have you evaluate some integrals, but sometimes if I say set up but don't evaluate, that means you can leave an answer like that. But we can find the antiderivatives, plug in the endpoints, and we'll get an answer. Again, what made this problem interesting? Well, first of all, we use symmetry. We use symmetry to cut the problem in half. We only found the area over here. We only found the area over here, and we multiplied it by 2. The other thing was that the curve, the height of the rectangle changed. The height of the rectangle from 0 to 2 was the blue curve minus the red curve here, but from 2 to 3 it changed. All right, so be aware of that. Okay. Okay, well now we're back to another problem. We'll just do a setup on this one. And here's the, if you can read my chicken scratchings here, it says find the area bounded by these 3 curves here. Bounded by y equal the square root of x, y equal x minus 2, and the x-axis. So what's the first thing to do? Correct. You wanted to draw it. Good answer. Good answer. Y equal the square root of x. What does that look like? Well, that's kind of like that. Okay. Y equal the square root of x. What's this y equal x minus 2 look like? Well, we'll put that in green. Well, you know, it has a slope of 1. It has an intercept of minus 2 here. That's going to go like that, maybe. I better make these things cross each other. Okay, and then well, what about the x-axis? That's the x-axis. So I want this area in here. Okay? I could do this thing a couple ways. A couple ways you might see this, and maybe you don't. If you integrate with respect to x, and if you draw your rectangles this way, okay, if you draw your rectangles this way, well, you might notice at this point right here, you've got a different integral. Okay? You've got a different integral. And if you integrate it this way, well, what's the height of this rectangle? That is going to be the square root of x minus, what's that curve? That is actually y equal to 0. So you could say that's the square root of x minus 0 times dx integrated from what to what? Well, it's going to start at 0. And where does that intersect there? Well, when is x minus 2 equal to 0? That's at 2. So you could go from 0 to 2 here, plus you got a second integral. And you got to integrate from 2 up to what? What's that? Where do those things intersect? Ooh, I might have to do a little work here. I can see it's going to be something clean like 4. It is, but let's just do it. We say, well, when's the square root of x is equal to x minus 2? Let's square both sides. I'm going to get x is equal to, when is x equal to x squared minus 4x plus 4 equal to x squared minus 5x plus 4. X minus 4, x minus 1. X equal to equal to 1. Something doesn't look right about that. Okay, so you see I got an answer here. I got an x equal to 4. X equal to 4. You might say, well, what happened to this? I stared at that a little. What about x equal to 1? Remember when I squared it, I created another answer. That really is. And when you put in 1 here initially, square root of 1 is 1, and 1 minus 1 is negative 1. So this is really the only solution. Anyway, we found that this point is equal to 4. They intersected at 4. So I'm going to go from 2 to 4 of what? Well, that's going to be the square root of x minus 2. Well, why is that tricky? Nothing really tricky about it. It's just a little, if you see the problem a different way, you might realize it could be easier. Let me do this. Let me see if I can, since I'm almost out of time, let's integrate with respect to y. Now I'm just going to draw my rectangle this way. Okay? And now I've got to change my functions. Well, that is not y equal x minus 2. That's x is equal to y plus 2. So now I've got x as a function of y. Now what about this curve? It's not y equal to the square root of x. It's x is equal to y squared. Okay? X equal to y squared. So what is the width of that? That now becomes what? Y plus 2. That's the outer curve minus the inner curve minus y squared. That is the width of this triangle. Well, what's the height? What's the height of the rectangle? Well, that's just dy. Okay, so if I put in dy here, and now the trick is what? What am I integrating from? What are my limits? It's y equal. Don't forget, y equals what? Y equals 0. Goes from y equal to 0 up to this point here. What's y? Well, remember, this value here is 2. 4. When you put in a 4, you get a 2. So this is y equal to 2. Okay? So my reason to point this out, this is a much easier, right? This is much easier. If you mainly just take the time and realize, if I cut this in y's, I only have to make one integral. And it turned out it was easy to convert from functions of y to functions of x's. So I show you that to realize you can cut these problems a couple different ways. Sometimes it's easier, sometimes it's harder. You get to choose. So in this video, I showed you how you could decide to make your rectangles either go on the x direction or the y direction. One way might be easier than another. I showed you how to use symmetry to make your integrals easier. And I also showed you to be careful if there's an intersection of your curves, you might need to change to have multiple integrals in order to define your areas. Okay, well that's it for areas between the curves. We move on to volumes now, and this is one of my favorite topics. See you soon.